Okay, today I will show you an interesting software. This software actually is free of charge. So I show you where you can get the software. So if you go to if you go to this CFI calculator, you Google for that. Under the informer.com, all these things, you can find this software that you can actually download it free of charge. Okay, so I think the version you get would be similar to this one. Okay, so let's just look at this one. Okay, so this actually is a free software. It's quite interesting software to use if you are actually have a training in the fire background. So you know a bit about the chemistry of fire and things like that. It's quite interesting to use actually. But this actually is not a CFD software. That means it's not. It does not simulate fluid fluid dynamics. It does not simulate like how the flow is for the when there's a fire, how's the flow. So that it doesn't do this. So actually it's a very simple, but it's actually a very rough estimate. So these are when you open it up, actually these are the few things that you get to use. The one that I always use is sprinkler activation, but I will show you the rest. I think it's quite interesting if you actually know these things. Okay. Flame height actually is the height of a fire. If you have a fire, when it's a steady state, all these things, because a fire can be dynamic, all these things. So actually, you can get an average height when there's steady state. You can get the height of the flame. So what does the height of the flame actually depend on? It depends on actually is what is burning. That means whatever fuel you have is called heat release rate. So this is the heat kilowatt heat release rate. Actually, it's like a design fire. Like you use it like when you design for a smoke spill, all these things. You need to know the heat release rate. From the heat release rate, actually, you can actually calculate the temperature of the smoke. So the bigger the heat release rate, the higher the temperature of the smoke. But this in material, this is like a flame height. Let's say if you have heat release rate, let's say like for this retail is about 5,000 kilowatts. For Tanum is a bit different. And then you need also a diameter. Let's say it's actually in the center. If it's atrium, it's the center. If it's against the wall, that means one side is wall. In the corner, there are two sides wall. Okay. So when there are two sides wall, actually the flame actually could be higher. So okay, let's say we have we can check. Okay, center of the room. Okay, let's say your fire, this is a fire diameter. Actually, you have to find out for yourself. You probably could Google the thing. Let's say I have a diameter of fire 2 meter, for example. So then it will actually calculate for flame height. So when I check the flame height, actually is about there are few formulas they use to calculate flame height. So they have a 6 meter under McAfee. NFPA they get 5.25. Hexastat flame you get about 4.9 meter. Okay, just remember this. Okay, now let's go back. Okay, we are in the center. The fire is in the center of the room. Let's say the fire is actually at the in the corner. Let's check the flame height with the same diameter that we have. What do we get? Also the same, but the NFPA one is a bit higher. Okay, 9.14. Remember 9.14? Okay, let's say we check it again for the center of the room. Calculate. So you can see that actually for the NFPA flame height, actually it takes into the consideration where is the fuel. So actually I would say that NFPA should be more accurate because actually it makes a lot of difference whether your fire is in the middle of the room, in the where there's one wall backing it up or two walls. So let's say, okay, remember these are 5.25. The other one that we have is in the corner is 9 against the wall. Let us check again. Okay, 6.93. So that's an increase. So you know that actually with the wall, all these things, it could actually make the flame goes higher because actually there's a direction where the plume can travel. Okay. Okay, let's say this, if you do not want to calculate, let's say you got your flame height, you don't know what's the heat release rate. So that means your flame height is something that you can see. So let's say you can see that this is for people with doing wildfire or something like that. So let's say he can see that is about 20-meter flame height, for example, and then a 2-meter diameter, then you can calculate what's the heat release rate. So this is the heat release rate. So actually you could see that actually there are quite some differences. It's 100,000, 70,000, 89,000. Okay. So that's just to show you how to use the thing. Okay, so you back to this one, then you can also actually calculate a heat flux. Heat flux is the amount of heat that's released per meter square. So let's say you remember that you have a fire. When you have a fire, you actually have 0.7 of the fraction actually is when we calculate smoke spill is actually convection. That's the thing that is actually taken into consideration when we calculate our mass flow rate, required mass flow rate of the exhaust. So for radiation fraction, probably is about 0.3. If convection is 0.7. Let's say you same thing, you have a 5 megawatt fire. Let's say distance between radiator is 2 meter. So this is the distance between radiator. That means actually is the distance. That means the nearest wall, how much heat actually it encounters. So let's say your fire is actually 5,000 kilowatt. Also, let's say it's in the center of the room, okay? And let's say your room is 10 meter, so that means it's 5 meter, okay? So just play around with it, and then you can see that it's actually 4.77 kilowatt per meter square. So this is the things that you can play with. So I guess that you can find out also what I think is interesting. You can find out, let's say if your house is on fire, roughly the size of the heat release rate. And then after that, you have a distance between two houses. Then you want to find out that whether the next house, what's the heat flux it gets. And then whether the next house actually, what kind of construction it has for the external wall, whether that heat flux will actually cause the fire to ignite in the next house. So these are kind of things that you can play with. So this is the other way around, the heat release rate. Let's say you got a heat release rate. So you got a heat flux. Let's say you know the heat flux at the other side. Let's say your heat flux is 20, I think 20 kilowatt. I think it's a flashover fire. Things can burn easily. Let's say you got 5 meter distance. Then you can calculate actually is, okay, this is the heat release rate. So actually you need this kind of heat release rate for actually the flashover to happen to, or not flashover, for burning to happen on the next building that's located 5 meter away. So either you can put back or you can go to home. So when you go to home, then you can go over to flash over. So flash over actually is a bit more complicated. You need to key in the room dimension. Flash over means that when everything in the bedroom starts burning, or in the room that starts burning. Let's say you have a living room that is like about 10 meter by 6 meter, for example, 6 meter. Then you have your room height is about 3 meter. Let's say that's opening means opening of a window opening. So let's say your opening is about, width is about, like, let's say 2 meter. Then let's say the height is about 2 meter. Opening height, I think, is to the, I'm not sure whether it's to the center. You need to check back again whether it's to the center or to the bottom of the windows. Boundary thickness is I think is to do with when you do all these heat calculations, all these things, sometimes you need to set up a boundary. So let's say your boundary you're using, let's say you're using brick. I think boundary thickness you can just put a bit. Let's say your brick actually is about 0.23 meter, okay, thick. Then you can calculate that. Then that's the kilowatt flashover. That, so you can see that. But actually, there is a big difference between all these prediction. It seems that this Thomas and Balakos will actually require a higher input, whereas the MQH method will require a lower. That means you have 7 191 kilowatt, it can actually bring to a flash over, but actually that is very small, 700 over. I would take this Barbara-Quast prediction, but you need to check all these the formulas. I'm not sure. I just know actually how it's going to be used. Fire growth. Fire growth, you have this term fire growth when you input the fire for your computer fluid dynamics or FDS simulation, CFD simulation. You normally need to put in the fire and fire size and how fast it grows to the steady state. So let's say your fire size actually, let's say you want it to grow the fire growth input. So at a time you want to find out at a time of 200 seconds what happened. Okay, then for slow growth fire at 200 seconds, all these things, then this is the heat release rate. Okay. And then for the kilowatt, the heat release rate for moderate is this, for fast is this, ultra fast is this, and mobile ultra fast. Let's play around. I'm not too sure this thing. Let's play around. Okay, now you remember this figure 117468187.6, which is actually quite a lot difference, but it's because it's a different fire. Just remember some of the figure. Okay, and then okay, let's say we have a time of 150 seconds. So let's say it's then you can see that actually is smaller at 150 seconds. Okay. And then this is the other way around. So if you got your heat release rate, let's say we normally do when you do calculation simulation is normally 1 megawatt in the computer. If you use a software as a CFast, which is actually free of charge, but it's a limited input. Normally it's about 1 megawatt. Then you can select your fire type, whether it's growing slowly, growing moderately, growing fast, or ultra fast. Let's say you go ultra fast. So this is the time for it to get to 1 mega. For it to get to 1 megawatt. Ultra fast. Back. This is a second, quite confusing. This is a heat release rate. This is okay, kilowatt heat release. Okay, this is the one. Okay. Okay, go back to home. Then the other one that you can play with is sprinkler. I like to play around with this sprinkler activation. Let's say you know that your design fire size. Let's say you're only designing a 3,000 kilowatt fire size, a small fire size. Then this is your sprinkler response time. Response time index. So for let's say a normal sprinkler is about 80 standard. Activation temperature, if you use red bulb, is about 69 degree. Distance above, let's say your sprinkler is installed like 4 meter above it, 4 meter, and then the radial distance probably is like a 4 by 3 meter. So it's actually a 2 meter, half of it. This is the ambient temperature. Let's say your ambient temperature is 27 degrees Celsius. Then this one I'm not too sure. I've not played around it. You calculate the thing. Actually, is your ceiling jet temperature. The ceiling temperature will go to 165, and your activation time would be 16.3 seconds. Okay, let's say you play around all these things. Let's say, okay, for example, you have like a very high ceiling. Let's say you got 6 meter. You want to see. Remember just now it's 3 point something, then you calculate this thing. It actually now it's 24 seconds. So it's more than 10 seconds. So as this thing goes your ceiling goes higher, your sprinkler may not be effective. Let's say you have a 14 meter. So you can see that the sprinkler would actually not activate because your ceiling jet can only reach 61 degrees Celsius. So that's a way to play around. You must know your design fire size and the height of the sprinkler and the distance from the fire from the sprinkler. Okay, so that's for sprinkler activation input. So even for fast response fire, just now it will not activate because it only go up to 60 degree Celsius, where else your activation is 69 degrees Celsius. Okay. So go back to home. Then you have your heat release rate. I think this heat release rate is almost the same as flame height. Let's say what? Okay, I haven't played with this before. So actually you need to know your mass loss. So that means if you are burning something in a calorimeter, how fast does it burn per meter square second? Then the heat of combustion is that the material is producing, whether it's like maybe like 47 kilojoule gram. Maybe this is actually the heat of combustion. You need to check. I think I'm not familiar with this unit. Then you have your length and width of the fuel that's burning all these things. Then you can find actually the standard heat release rate. So this one actually you can play around. You just Google some materials, let's say wood or something like that. You Google and put into it and see what you can get. Okay. Then you have your time to ignition. This is interesting. Time to ignition, let's say your temperature around is 25 degrees Celsius. Then let's say I want to know I've got like almost a very high 20 kilowatt. I think it's almost like a flashover flyer. Let's say the ignition temperature is 200 degrees Celsius. Let's say it's actually a wood or something like that surrounding the fire. Let's say it's 200 degrees Celsius. Then you need to key in the thermal inertia. I can't remember the thermal inertia of wood. Just let's say that, for example, 3, I'm not too sure. Just see what it is. So it's actually time to ignite is 180 seconds. So this one you can play around. But you need to Google this heat flux. It's okay. You need to Google the material. Just now we can calculate the heat flux. So you need to know the ignition temperature and you need to know the thermal inertia of the material. Okay. So this is what you can do with a CFI calculator. So with this, I will actually end my recording. Okay.